Ever wish you could just order up a new material? Like,
Uh-huh.
call up and say, I'll take a new solar panel material, extra efficient, hold the pollution.
Well, that's kind of the promise these material acceleration platforms hold, MAPs for short.
All right, so MAPs. These are basically robot scientists cooking up new materials in the lab.
That's the idea. We're talking robots and AI speeding up the process of discovering and developing new materials.
Okay, I'm intrigued. Now, my sources mentioned this system called OCTOPUS. Is that one of these robotic scientists or what?
OCTOPUS is actually an entirely new operating system for these MAPs.
An operating system, so like the brains behind the whole operation.
Exactly. And what's really cool is it's built for multiple researchers to use at the same time.
Hmm. So like multiple chefs all trying to use the same kitchen at once.
Yeah. And that's one of the big challenges OC2PS solves, making sure everything runs smoothly. But before we get into that, let's break down how MAP actually works.
Okay, lay it on me. What are the ingredients in this recipe for material discovery?
Well, you can think of the MAP as having four key components. We've got the platform, the modules, the tasks, and the actions.
Platform modules, tasks, actions. Okay, break that down for me.
All right. First, think of the platform as a state-of-the-art laboratory. You know, your high-tech kitchen with all the gadgets you could ever want.
Okay, I can picture that. Now, where do these modules come in?
Modules are like your specialized cooking stations. So you might have one for synthesizing materials, one for analyzing their properties, another for testing their durability, and so on.
Gotcha. Each module is like a specialist in a particular type of experiment.
Right. Now, within each module, you've got specific tasks that need to be performed. Think of these as the steps in a recipe.
So measure ingredients, mix, heat, things like that.
Precisely. And finally, you have the actions, which are the precise movements carried out by our robot chefs.
Aha, so like picking up a beaker, pouring liquids, setting the temperature. These are the actions that bring the tasks to life.
You got it.
All right, so platforms, modules, tasks, actions. Got it. These are the building blocks of any MAP, and then we have OC2PS layered on top to manage this whole system.
Right. OC2TS is the conductor of the orchestra, making sure everything works together in harmony.
So if I'm a researcher, how do I actually use OC2PUS to run an experiment? Do I just walk up to the robot and tell it what to do?
Well, not quite. With OCTPS, you actually submit your request through an interface. This is called the interface node, the first part of the OCTPS system.
So it's kind of like online ordering for science experiments.
It's similar. So you basically tell the system what you want to cook up, and then the interface node sends your order to the master node.
And the master node, this is the brains of the operation, right?
You got it. The master node is like a super efficient project manager. It schedules all the jobs, allocates resources, and most importantly, prevents those robot collisions we were talking about.
Okay, collision avoidance. That's a pretty important feature when you've got a bunch of robots running around a lab. How does OCTPS actually do that?
It uses something called masking tables. Think of it like a set of rules to prevent chaos in the lab.
So before a task even starts, OCTOPUS checks its virtual rule book to make sure everything's safe.
Precisely. It's like having an air traffic control system for robots, making sure no two arms try to occupy the same space at the same time.
That makes sense. But what about when multiple researchers need to use the same equipment? How does OCTOPUS handle that bottleneck?
Ah, that's where the real magic happens. Let's say you need to use the batch synthesis module, which has a robotic arm for handling chemicals, but another researcher's already using it for a long reaction.
So now we've got a bottleneck, a cue for the robot arm. Does my experiment just have to wait until that other reaction is finished?
Not necessarily. OCTOPS is smarter than that. It can actually sneak in other tasks during those downtimes. So while your chemicals are reacting in one module, OC2PUS can start prepping your next experiment in another module, maybe getting your samples ready for analysis.
So it's like multitasking on a lab-wide scale.
Exactly. Octopus is all about squeezing every bit of efficiency out of the system.
This is starting to sound seriously impressive. But what about all those limited resources you always hear about in labs? Expensive equipment, limited space. How does OS2PUS deal with those constraints? So we've got all these robots working in modules, but lab space is always limited. How does Octopups deal with that?
It's a bit like a game of Tetris, actually. Octi2U uses this closed packing schedule algorithm to maximize space.
Okay, a Tetris algorithm. I like the sound of that. Tell me more.
All right, picture this. You need to run an experiment that requires 8 vials. but the stirrer in your module only has space for 4.
So now we have a space problem.
Exactly. Instead of waiting for the entire stir to be free, the algorithm gets clever. It splits your experiment into 2 batches of 4.
So it's like fitting those smaller Tetris blocks to fill in the gaps.
You got it. The first batch runs, and then as soon as there's space, the second batch is slotted in. No time wasted waiting for a large chunk of resources to become available.
Smart. So it keeps things moving. And this is all part of what makes OCTOPUS so efficient.
It's a big part of it, yeah. This closed packing schedule works with the user optimal scheduler we talked about to create a super efficient system.
Okay, user optimal scheduler. That sounds like it's at the heart of what makes OCTOPUS so special. But just how much better is it than running experiments the old-fashioned way?
Well, the researchers actually compared it to the traditional first-come, first-served approach, and let me tell you, the results are impressive.
Okay, I'm all ears. Hit me with those results.
All right, so the user optimal scheduler really shines when it comes to job waiting time. That's the time an experiment has to wait in the queue before it can actually start.
Oh, I can only imagine how frustrating that waiting game can be for researchers.
Exactly. And the user optimal scheduler minimizes that wait time. It's all about squeezing every bit of efficiency out of the system.
So it's like getting express service for your research. I love it.
Right. But, there's always a trade-off. The researchers did find a slight increase in something called job turnaround time.
Job turnaround time, huh? What exactly is that?
That's the total time it takes for an experiment to run from start to finish. So from the moment you hit submit to the moment you get your results.
I see. So the experiments themselves might take a tiny bit longer overall.
It can happen, yeah. And you're probably right. It likely has to do with the closed packing schedule. By splitting those tasks into smaller batches, there might be a bit more downtime overall.
It's like those extra few seconds it takes to strategize in Tetris and fit all the pieces just right. A small price to pay for a much better outcome in the end.
That's a great analogy. And the researchers definitely agree. They argue that this minor increase in turnaround time is insignificant compared to the major time savings from reduced waiting times.
Okay, I'm sold. But let's shift gears for a second. Say I'm a researcher just setting up a brand new lab. How do I even begin integrating all my equipment with this OCTOPUS system? It sounds pretty complex.
Well, that's where Copilot comes in. One of the things that makes OCT2 so futuristic, it's like having an AI assistant help you set everything up.
An AI assistant for lab setup. Sign me up. Tell me more.
So Copilot uses GPT, that same technology behind all those AI chatbots everyone's talking about these days.
Wait, GPT? That's the thing that can write poems and compose music.
That's the one. And now it's helping researchers set up their labs.
Mind-blowing.
Yeah.
So how does this all work?
Basically, you tell Copilot all about your new module, like what equipment you have and what tasks you want to run, and it actually recommends how to integrate all of that into the OCTOPUS system. Pretty neat, huh?
That's incredible. So it takes all the guesswork out of the setup process.
Exactly. And it even generates the code and configurations you need.
It's like having a robot lab partner that can do all the technical heavy lifting for you. This must be a game changer for researchers who aren't coding experts.
Absolutely. And there's another cool thing about Copilot. It learns from your feedback, so its recommendations get better over time.
So it's like having a lab partner that's constantly learning and improving.
Precisely. And that's really what makes OCTOPUS so revolutionary. It's not just about automation. It's about collaboration and accessibility, pushing the boundaries of what's possible in research.
So we're not just talking about faster experiments. We're talking about a whole new way of doing science.
Exactly. It's about democratizing access to these powerful tools and fostering a more collaborative research environment.
This is all very exciting.
Yeah.
But this technology is still pretty new, right? What are some of the challenges the researchers still need to address? So where do we go from here? What are some areas ripe for improvement, version 2.0 of OCTOPUS, that sort of thing?
Well, one thing they're focusing on is the user interface.
Makes sense. What are they thinking?
Right now, it's all command line based, which can be a bit much for researchers who aren't, coding wizards.
Yeah, if you want people to embrace a new tool,
Yeah.
got to make it user-friendly.
Exactly. So they're working on a more intuitive, web-based interface, something anyone can pick up quickly.
Okay, that makes sense. What else is on the to-do list?
Data management is another big one. They want to make OCTOPUS more flexible in the kinds of data it can handle.
Like a universal translator for scientific data. That would be huge.
Right. Imagine being able to seamlessly integrate data from all sorts of experiments, no matter the equipment used. That's the dream.
Wow, the possibilities are pretty mind-blowing. I mean, where does it stop?
Well, they're even exploring things like extended reality, virtual reality and augmented reality in the lab.
Hold on. VR and AR for science. That sounds straight out of science fiction.
I know, right? Picture this. You put on a VR headset, and now you can control the robotic arms remotely.
Okay, that is pretty sci-fi. And cool.
Or imagine using AR to overlay complex data visualizations right onto your experiment as it's happening.
It's amazing to think how much this kind of technology could revolutionize research.
It really is. And the coolest part is we're just getting started. With AI and robotics advancing so fast, who knows what the next generation of MAPs will bring?
It's exciting and a little bit daunting at the same time, isn't it? This technology could really reshape the world in some big ways.
It definitely could. And that's why I think it's so important for everyone to understand these developments. The future of research is going to be collaborative, automated, and immersive.
Yeah, it's not just for scientists anymore. It's something we all need to be aware of. And if this deep dive has sparked your curiosity, I highly recommend checking out the links we've provided.
To the OCTOPUS GitHub repository and the article itself. Dive deeper into this fascinating world, see where it takes you.
Maybe you'll be the one submitting that groundbreaking experiment to an OCTOPUS system in the near future.
I hope so. Until then, keep exploring, keep learning, and keep diving deep.